Hi and welcome to episode 3 of our particles course. This is Manuel, and in the last 2 episodes we built 2 practical examples using particles. So with this episode it's time to dive into some theory. I know this is dry material, but it is necessary because the setups will get more complicated and we have to build up a clear understanding what exactly is happening with simulation. So I built this file for you that clearly shows you what exactly is happening. So let's dive in and build some intuition on how a particle solver is working. What you see here is one red particle, and I animated the particle. This is a one-dimensional example, so it's only animated in the y-axis. And it is animated traditionally. Instead of using a standard f-curve, I used a mathematical function, but the principle is exactly the same. This curve defines the movement of the particle. So this x dimension is the time axis, and this here is the value axis. And you see that the particle always has a y value similar to this graph here. By the way, this is a hyperbola. I used this function here, 2x minus 0.5 to the power of 3. That is why I have this inflection point here. I just chose this because it's a little more interesting than a parabola. So we have this animation. But we can ask questions about this animation. For example, how fast is the particle going? So we are interested in the speed of the particle. And we can calculate the speed, fortunately, from this curve here by using the differences quotient. I built a differences quotient here. This is just rise over run. So we consider the change in x, or the time axis, and the change in y, or the function value. And then we divide the change in y by the change in x. And this gives the slope of this line. At the moment the slope of this line is only more or less similar to the curve. But what happens if we narrow down the distance that we travel on the x-axis? You see, the smaller this little triangle gets, the better this line approximates the slope of our curve. And the slope is exactly the speed of our ball. Mathematically speaking, this slope is the first derivative of this function. So the first derivative gives us the speed of our ball. We not only are able to find the derivative with this differences quotient, but we can find it analytically. And this is the exact function that is the first derivative of this function. And the graph of it looks like this. It's a parabola. And this parabola exactly shows the speed of the ball, or the slope of this function here. So, at the very beginning, we are quite fast. Then we slow down a good bit until the motion comes to a halt. And then we increase in speed again. So we accelerate. Watch again. We decelerate. Then we halt. Then we accelerate. So that is the speed that this ball has. But what about the rate of change of this speed function? Well, the rate of change of this function is the derivative of this function, and that is acceleration. So, mathematically speaking, this is a formula for the second derivative of this function, and this is a graph. The change in speed is the acceleration. And you see, we are first decelerating and then accelerating, because this graph first is negative, and then on this inflection point it is positive. So these two derivatives give us a lot of information about the animation of this particle here. But how is this useful for particle simulation? Well, because particle simulation is exactly the opposite of traditional animation. Instead of starting with the position of our particle, and then from there finding the speed and the acceleration, we want to start with the acceleration, put the acceleration into the system, and then compute the speed and the position from here. But how on earth do we know about the acceleration of particles? Well, there is this formula here. F is m times a. This is Newton's second law, and it tells us that the force is the mass times the acceleration. And with particle simulation, we can assume that the mass of the particles is just 1, so it goes away, And that means if the masses are 1, acceleration is force. And that means we can put forces into our system. And these forces will be acceleration. And then from these forces, we can calculate the speed. But it is important to note that in 3D space, we are dealing with vectors. So the acceleration in 3D space not only has a magnitude, but it has a direction too. And speed is not a vector quantity, but velocity is. So we are not dealing with speed, which is just a scalar quantity, but we are dealing with velocity, and that is speed plus direction. So the magnitude of the velocity vector is the speed. Great. So what we can do now that we know that, we can just define forces. These forces will create acceleration, and then we can compute the velocity from the acceleration, and from the velocity we can compute the position. And that is what simulation is all about. Mathematically speaking, this process is called integration. Creating an integral of a function is the same as finding the antiderivative. So it's the reverse process of finding the derivative. So what we have to do is we have to do integration. We have to create an integral. And that can be done analytically if the function is very simple, so we can go from here to there by using integration. But with a standard particle system, this is way too complicated. All these forces and all these particles, that's too much for finding an analytical solution. So we have to do something else. Well, if you consider this acceleration function here, this here is the rate of change of the velocity. So the slope of this line is defined by this function here. That means if we have this function, we can create a line with this slope. So what if we start at our initial condition here at 0? We know the exact velocity of our particle here. And then we use this line to just travel a little bit along this line and add this to our initial velocity to find the next velocity. And then we do this again, and then we do this again, and then we do this again. So in every frame, we just add a portion of the acceleration to the initial velocity to find the new velocity. And that is numerical integration. And the method to do this is called Euler's method. So we can just add all these tangents together to approximate this curve. Let's do that. I prepared this for you. It is here. And this is Euler's method. So look at this. This blue line here, again, is the tangent line to this yellow function. And the slope of this line is defined by the acceleration function. But what happens if I increase the points? So now we are going piecewise. First, we are going a little bit along this tangent line. Then we add the next tangent at this point, and then the next tangent, and then the next tangent, and then the next tangent. And we always do a little time step. So we step in time, then we read the value of the purple function, create this vector here, and add it to our initial velocity. And you see that this starts to look a little bit like our function here. And what happens if we increase the points on this line? And we can do this by decreasing the time step. And if we do so, you see that the approximation gets better and better and better, and the more steps we are using, the better the approximation gets. And that is exactly how a particle system computes the velocity from the acceleration. So it takes the acceleration and then multiplies the acceleration by the time step and adds it to the initial velocity. And in the next frame, it takes the velocity from the frame before and again multiplies the acceleration by the time step and adds it to it. And by adding up all these little linear lines here, we can approximate the function. And of course, it is not perfect, but it is good enough. And there are better methods than Euler's method that converge faster, so that approximate this function better. But Euler is very fast, and that is why it is used for particle simulation, because it is precise enough. So, by using this numerical integration, we created the velocity from the acceleration. What's next? Well, next is to do the same thing again. Now, with this velocity curve here. So now we are doing exactly the same thing, but with the velocity. So you see, if I quickly make this visible, this green vector here is the tangent to our original function. And if we use this and then add it up in every time step, we can approximate the position function, just as we approximated the velocity function. And you see, as I do more and more time steps, this approximation gets closer and closer to the real thing. And that is exactly how particle simulation is done. We start with the forces. The forces are creating acceleration. The acceleration is integrated to find the velocity function. The velocity is integrated again to find the position. And this position is where our particles live. So now let's evaluate our result. I animated this ball from frame 0 to frame 121, 5 seconds. And that means for doing integration, I have to do 121 time steps. And I prepared this. Let me deactivate this stuff here for you. I prepared this here. This is 121 time steps. So one addition of a little slope line here per frame. And if I use this integration here to drive the position of this faint looking red ball, you see the result of the particle simulation. You can compare it to the original animation. And you see it is not exactly the same, and that is due to numerical error, but is very, very similar. And that is how particle simulation is done. So instead of putting in the position, you use the forces and drive the particles using the forces that are then creating the velocity, and the velocity is creating the position. And the big advantage of this approach is that you can create a physical system to drive your particles instead of defining the positions for each and every particle. Watch again. Not exactly the same, but very close. So great. Now let's build our first pop solver from scratch inside of Houdini. Okay, let's start with a geonode like every time and dive inside. And inside let's create a grid. And let's make it 1 by 1, like so. And now append a scatter to create our particles. Here we have them, and we want to create only one single particle per frame. But we want to create a different particle in every frame, so go to the global seed and put $F here. So the global seed will change with every frame, and so will the particle. So if you move the time slider, you see the particle dancing around. Let me turn on point numbers. You see? Great. So now that we have a particle, let's create some initial velocity. So lay down a VOP, point VOP, because I want to use some noise to create the velocity, and call it set initial velocity. Because remember, we need initial velocity to start our integration. Dive into the VOP and lay down an anti-alias noise, but set the anti-alias noise to output 3D noise. So input is 3D and output is 3D. And connect P to the position. And let's promote the amplitude to be able to change it one level up. And because we only want velocity vectors that are somehow pointing upwards, we want to fit the result. So append the fit range here and fit it from -1 to 1. In all components, -1 to 1, that is what the noise outputs. And then in X, it will remain -1 to 1, and in Z, it will remain -1 to 1. But in Y, it will be 0.5 to 2. That makes sure that the vectors are always pointing upwards. And now connect this to v for velocity. Velocity is a standard attribute, so it's already built in. Now we have some initial velocity. If you click this visualizer here, you see this little green line here indicating the velocity. And now let's lay down a force. And a force, as we learned, is nothing but a vector. So lay down a point wrinkle and call it gravity. And maybe you remember, or you can look it up on the internet, that the gravity force is around minus 9.81 on the surface of the Earth. So let's create a vector, v at force, and this is a standard attribute too, it is built in. And let's set it to be 0 in x, minus 9.81 in y, and 0. So this vector is our gravity force. Now that we have an initial velocity and a gravity force, it's time to do our integration. So another point wrinkle it is. Append another point wrinkle and call it integrate force to velocity. Make it visible. And the code for this integration is very, very simple. It's just add v, that is the new velocity, should be add v, and that is the old velocity, plus add force, as we learned, force is acceleration, and now times the time step. And the time step can change. But fortunately, Houdini provides us with a standard attribute that always gives us the current time step. So the time interval that is one frame. And this attribute is called time inc, like so. And a semicolon, then the error disappears. So this is our first integration step, as explained before. The new velocity is the old velocity, and on the very first frame, this will be the initial velocity, plus the force vector times the time step, time inc. So after the step, we have a new velocity vector. Let's make the velocity visible, and let's see. And you see, well, the velocity vector is changing. Great. So the next step is to find the position from the integrated velocity. So append another point wrinkle and call this point wrinkle integrate v to p, because we want to find position from velocity. And here we write something very similar. At p, which is a new position, should be at p, which is an old position, plus at v, that is the integrated velocity vector, and again times at time inc, and that is the time step. And now you see, if I activate and deactivate this, our particle moves, because it moves along its velocity vector. So that is our basic pop solver. It's just that it's not solving, because it is only executed on the very first frame. We have to make it solve, and we can do so by using a solver node. The solver node is just a DOP network wrapped into a subnode. So let's put our initial velocity into our solver, and all of this business here, we cut it and we move it into our solver, in here. And in here we have this previous frame node that always serves the previous frame of the simulation. And now we want to connect our solvers here. And we connect it to the previous frame. But we want to take into account that we are creating particles all the time. And everything that is connected to the first input of this solver node comes in over this node here, input 1. So after we solved the very first particle, it's time to add a second one. So just lay down a merge, and just merge the result from this first integration step with a new particle. So the new particle does not get solved, it is just added. But in the next frame, both particles will come out of the previous frame node and will get solved. Now we can go back to frame 1 and we can press play. And this is very fast, so let me turn on the stopwatch. And you see, this is our very first self-made particle simulation. The particles are being burst on this grid with the initial velocity that is pointing upwards, and then our gravity force is moving them back down. So, one last thing is to add a switch, because we don't want to do the solving on the very first frame. Instead, we just want whatever comes in on the very first frame. So go to the switch and to this select input field here and put in the expression $f == 1. That means on the very first frame, with the frame number 1, this node will just read whatever comes in over input 1, and after that all the simulation begins. So if we test again, this is our particle simulation. It is very easy, and now you exactly understand why it is working. But let's quickly check if we really build a pop solver. So lay down a pop network here and feed in our particles. Dive inside, make it visible and dive inside. And inside go to source first input, and instead of scatter onto surfaces, switch this to all points, such that the particles are created as they come in. And go back to frame 1 and let's see what this gives. And this gives particles rising due to the initial velocity. So let's add a gravity force here, as we did on our custom built solver. Gravity force. This gravity force uses a more precise value, minus 0.80665. Let's make 9.81, like we did on the custom solver, like so. And let's see what this gives. So that is a particle simulation that looks quite similar. Let's go to frame 47, say, and let's compare. And both of them are nearly identical. The difference is probably in the pop network, under birth, the jitter burst time. Set it to none. And let's compare again. Let's simulate some particles. And now you have it. Without the jitter burst time, both results are exactly the same. Let's append a color node to our solver and color the particles, say, red. And let's append a color node to the inbuilt pop solver, and let's color the particles blue, and now, or green. And now let's merge both. And you see that the results are absolutely identical. So that proves, let me switch again, red, green. Let me make the particles a little bigger for you to see them better, like here. So green, red, green, red. It's exactly the same thing. So the inbuilt pop solver does exactly what we coded here, no more. And of course the pop solver has a lot of functions built in, a lot of features, but the basic integration, the basic moving of the particles is exactly what I showed you today. And if you quickly allow editing of content on the pop solver and dive inside, there is a plethora of nodes in here, but the most important node is here, this enable integrate positions and then integrate positions, this gas integrator. This is in charge of integrating velocity to position. And if you click this microsolver, you see that its simulation method is set to Euler. And that is why it is exactly doing the same thing as I did in my wrangles, because I'm just implementing Euler. So, in this lesson, you learned how exactly the pop solver is doing its job, and we proved that this code is doing exactly the same as the pop solver that is built in. And that means that we now understand exactly how particles move, and that it is a difference if we set the force or the velocity or the position directly, and that we can do all of these three things to influence our particles. And we will do so in the future. So thanks a lot for listening. I hope you learned something. I hope you enjoyed this topic, although it is dry and mathematical. But with the next episode, the fun starts again and we will build more practical stuff. So see you next time and thank you.